Hi. So recently I've gotten into graphics programming a bit, and I had this issue where I introduced collision detection in my code. And the default implementation that you usually do when you're a beginner, most likely, is to do the open squared implementation. We are checking each object against each other object. And it turns out that this is very inefficient. It was the bottleneck of my application. So then I thought, okay, what else can I do to slightly improve this? And it turns out that the simplest thing you can do, and it's very easy to code, is to just use basically a hash map where you are putting each object into like its own grid, and then you are only checking the objects in that one grid. So the idea here is that you don't want to check an object against another object that is very far away. You only want to check in its neighborhood. So let's see how this is implemented, starting from a very scratch, hello world Raylib application. I will be using Python, and then we'll see exactly how we can build this on top of the simple open squared implementation. All right, so what I'm using here is just basic Python. So for example, I implemented the Raylib wrapper. So Raylib is this C library, but you have like Python implementation of it, so you can call the C code from Python, and this is usually what you do with Python. You just call like lower level libraries from your Python code. And I use Python just because I'm more familiar with it. I've been programming in Python for years. So whenever you have a Raylib application, you basically do init window. Init window, which basically instantiates a window for you. I think it uses SDL behind the scenes. So for example, let's do it 800 by 800, and let's just put like a random title here, like collision detection. This application, this particular application, will be a 2D, but then at the end of the video, I'll show you how you can extend this to 3D, so you are not limited to 2D implementation. So I also like to put this thing, the shebang, in Python. So that means we can run this. So right on the activate. And as you can see, like we call the Raylib library. It doesn't stay, because in order to make it like stay, you need to have like a while loop. So how I usually do this in Raylib is to have this while Windows is not closed. So basically, window should close. And then you like do basic drawing stuff. So for example, you use clear background. I will link the Raylib documentation, but you can find it very easily. It's a great library for like graphics programming. It's very low level, but it's like at the right level. It's just above OpenGL, which is perfect if you want to like understand how things work. So in clear background, you use a color. So for example, there is this ray white, which is like the full tone. And yeah, what else do you need to do here? So basically, while not this, and you can like for example, you also need to do begin drawing, and then drawing here. So and drawing, I think this is all you need to have like a basic thing. All right, so now let's start drawing like some objects. So for example, in order to draw like a rectangle, a basic rectangle, or a circle, let's start a circle because we're going to use circles here. You can do draw circle and do X and Y. So that's like the coordinates. So we're going to 100 to 100. Use the radius, let's say 30, and then you put a color, so let's say black, and you get like a circle. Another thing that I like to do, and I will be using this in this implementation, is I also want to have like an object on my mouse. And the reason I want to do this is because I want, for example, to do collision detection with my mouse against other objects. So in order to do this, you can get the mouse position. And there is a function in Raylib that does this for you. So it's get mouse position, I think. Get mouse position, yeah. And this is like a structure. So it's a C structure. It gives you a vector 2. So in order to use it, you need to access X and Y because of Python mostly. And you can do basically another circle, excuse me. And you can use mouse position .x, mouse position .y. Again, radius, we can put it 30, and yeah, okay, you need to convert those to integers just because. And now we have like an object where the mouse is, and another object which is static that I put earlier here. Okay, so the next thing that we want to do here is to check if the circle that we have created with our mouse, so basically this one, is intersecting with the other one. So basically to check if they are colliding, right? So if these two are like objects that are like floating in space, we want to see if they are colliding. So how can we do this? So for two circles, it turns out that the algorithm is actually very simple, right? So you have a circle is defined by the radius, which is like the distance from the center to like the edge, and the position, so the center position, x and y. So you have like three numbers, the position and the radius. And if you have two circles, basically you have two centers, center 1, center 2, and two radii, which is like radius 1 and radius 2. And it turns out that if you do the distance between the centers, and they are greater than the sum of the two radii, that means the object is not colliding. If the distance between the two centers is smaller than the sum of the radii, so in this case the first one would be here, the second one would be like here, so the distance is greater, that means is smaller, that means they are colliding. So let's see how we can implement that. So the first thing that we can do is we can have like a distance function. So let's call it just dist, for example, between 2 points. So we want to have point 1, let's say p1, which is coupled in int, or maybe float. This is just type hinting because it's Python, but still want to use type hinting just because it makes your life easier. And in order to have the distance of like 2 points in space, you basically do the following. You do p1 minus p2. So let's say this is res. This is the x coordinate squared plus the y coordinate squared, p1 minus p2 of 1 squared, and then you do the square root of this. So this is just the distance of 2 points, like the Pythagoras theorem, right? You do have the x and the y, and this is like the hypotenuse, and the hypotenuse is the distance in 2 dimensions, and you do basically the square of this thing. You need to import math as well, there, and I think you can just record it. This is basically a distance. So let's see if that works. So for example, if I were to put like the mouse position minus this thing, so for example, I would do like how would I do this? So print distance between what? So P1 would be 200, 200. P2 would be mouse position, x mouse position of y. For example, let's see if this works. You can use this little thing. Let's have like some decimals here. So let's see if this works. P is supposed to be 1. Okay. So this is the y coordinate. And as you can see, now this we have the distance between like the center of the mouse and the center of that circle. And as we get closer and we get closer, basically they start like the numbers get smaller, and when they're overlapping, the distance is exactly 0. Let's see if I can make it 0. Probably not. All right, that's it. And then the further away, that's the distance increasing, so the function works. Right. Now let's see if the two are colliding, right? Because as we said earlier, like the check is basically to see if the distance is greater or smaller. So for example, if you want to see if the two things are colliding, all you have to do is to check the distance if it's smaller than the radius. So let's do that. So let's call this function maybe check collision, circle, for example. And as we said, like the circle is defined by a center. So maybe let's call it C1 for center, float, radius 1, which is like the radius. R2, and this returns a boolean, right? So it returns true or false, right? So let's just follow this implementation. So basically we will call a return distance of C1, C2, so the two centers is smaller, right? So it's true if it's smaller, and the sum, we'll just call it around or something. All right, so continuing with this example, for example, we could color one of them if they are colliding. So for example, we could do it like this: color equals black, and we would say maybe let's put mouse position in a separate variable. So how would I do that? Like T1 maybe. C1. So T1 is this. R1 is 30, right? R1, and then let's call this maybe C2 and R2, and C2 is this center, R2 is also 30, and now if check collision between the first and the second one, so C1 R1, C2 R2, color is red, and we will put color here. So what we have done here is basically put variables for the center of the mouse and the center of this object that we are drawing, and if the mouse is colliding with the object, then we draw the object red, and let's see if this works. So technically now it should get red, and it does. Okay, we can make the mouse red as well, but yeah, we're not going into that for now. Okay, so one thing that I usually like to do before going to more objects and doing more complicated stuff, and I keep finding myself doing that, and I'm not sure if it's a good path or not, is basically to create this small class, which I just call scene object, which has a single scope, and that scope is to basically abstract a bit these objects, these shapes, so I don't have to work with raw variables. So this isn't supposed to be like a very OOP like implementation, so it is just a simple wrapper. So usually what I like to do is put here like object type, and then just all the other arguments, and I just save those as is, object type, self.args equals args, and I like to have a draw function usually, which in this case would be something like if object type is circle, and we'll create like a special implementation for it. We just call this thing, but we are using self.args. And color. Usually I also like to pass color separately. It doesn't necessarily a necessity. Have to put the type hint for relib stuff in quotes. This is just a Python issue, to be honest. Like the wrapper is not properly made, so it would crash otherwise. And we can also add like an assert here. So object type circle, just so we don't try to create other stuff. So the draw function will do nothing. And I usually like to have a list of objects. So let's say object or scene objects. And just call scene object circle. And then I use this ones here. So 200, 200. This is the center. The radius is 30. And usually I also like to have like an extra object. So let's just add it variant here, which is just the mouse. And this is just like a little bit of boilerplate, so we can make like the main loop a bit nicer. And this is also, so this is like a placeholder for the mouse. I just put it on 0, 0, 30, so that's the top left point. And now let's update it. So basically we have the mouse position at every frame. So this is like the main loop. We get at every frame we get the mouse position. So we need to update this last object. So that's just -1 arg 0 equals mouse position of x, mouse position of y. And then basically what we do is for object in objects, object.draw, and we get rid of all of this. We can check, we can keep this. So for example, if we want just to have, so if we use color here, and we can keep this check basically like this. So color is black. Color is black, and if check collision circle circle between the first object, so that would be like object. Actually, usually I do it like this: scene object of 0, scene object of 1. So we know the mouse, or maybe we can just do the last one. Color is red. Red, and then we do that. Get rid of this, and usually I also have like this check collision thing, because this is like low level math, right? But you also want to have like a global one, so check collision, which kind of accepts two objects, object 1, scene object, object 2, scene object, and it does this little dynamic dispatch in there. So it's just like foreshadowing for me, adding more types of shapes, even though maybe in this video we'll only use circles. This allows you to add like rectangles and so on, and like more things, like convex hulls. But here you just do it like this. So if object type is circle, and object type is circle, then we just return the underlying function. So that would be like object2.args. Really, that's not how you do it. So you need to do the center. So it's object1.args02. R1 is object1.args2. C2 is object1.object2 of args02. R2 is object2 of args. All right. And otherwise, if you can like the array is not implemented there, object1.type, object2.type, something like that. Cool. So now we basically have the same thing, but we have this list of objects which will be used. We have the mouse as the last object, so this is like we'll always keep it like that. And now let's see if this little refactoring worked. You cannot do that with a tuple, so in order to you can like convert this to a list. An integer is required. All right. So for the draw thing, right? So maybe you can do it like this: int value1, value2, and then yeah, you have the colors and you have the two objects. That's good. All right, cool. All right, so the next natural thing to do here is to create more objects, because this is why we created this is why we abstracted this a bit. So now we have like a list of objects, so we can just add like 3 more objects. And for example, we put like 2020, we can even change the radius to make it smaller or bigger. We can put like another 100, maybe one somewhere in the bottom, so 500, 300, with a radius of 100, for example. So this is just more objects. Since we are doing a for loop here, it should render all of them. And yeah, and also, okay, you can see right now we are drawing all of them if the first object is colliding with the mouse. So let's maybe change that thing. So we check each object against each other object. So actually we check each object against the mouse first. And if the two are colliding, then we are drawing them. So in order to do that, we should iterate over them. So maybe we have like a vector of colors, for example, one for each object, pretty much, times in objects. All right, so in order to do that, for example, we would do it something like this: enumerate colors. So for object in scene objects, maybe -1, because we want to check against the mouse, and the mouse is the last one. And if check collision between the ith item, so basically the ith shape is colliding with the last one, then we are basically coloring it red. And we need to do enumerate, and this is 0 -1, so you just all except the last one. Now we should get collision against each of them, because again the collision function is very simple, and as you can see, like, it doesn't depend on the radii, it doesn't depend on anything, it works. You can do it against the mouse. Now, as I said earlier, we are finally at the point where we can do this O(n) squared implementation, meaning that we don't want to check the mouse against all the other objects. You want to check all the objects against all the other objects, because in a real application, like, the objects would be moving, like we'll have like bouncing balls or anything, or I don't know, like particles, and you want to see if, for example, a bullet touches a player or something like that. So you need to check all the objects against all the other objects, at least all that are movable, for example, or collidable, depends on how we implement it. And in order to do that, you will just have to do this O(n) squared implementation. So let's do that. We will still keep this one, so basically this is the color, and we will just basically color it red if it's colliding with any other object, or keep it black if it's not. So for example, in order to do that, we will go for object in objects. Actually, it's with an I here as well. And then you have for G object doing all the other objects. And if check collision basically between object and, let's call it object 1. It's obvious, object 1, object 2. That means both of them basically should be red. Color of I, color of j. Now, there is a problem with this implementation, and I will show you exactly what the problem is. All of them are red because they are also checking against each other. So in order to not do that, you need to do if I equals j. Now, basically it's the same code as before, but in a more generic way. But the problem, as you can see here already, is that you have this O of n squared implementation, and this is basically what we want to get rid of. We can also like factor this, and actually I will do that immediately. Okay, so the next thing that is natural to do here is to actually make a function out of this, and usually I just call this get collisions, which simply receives all the scene objects. So let's just say objects here, which is a list of scene object. And what this returns, usually what I like to return is the following. I like to return the object and all the object is colliding with. This is optional, you can also do it the other way, but this is kind of how I like to do it. So basically, for all the objects that have any sort of collision, we return all the objects it's colliding against, right? All right, cool. So in order to do that, we can literally just copy paste this thing here. Scene objects, because it's like that, so we go like there. All right, so we have a variable called result, which is an empty dictionary, and if those two are colliding, basically you would do something like this: res dot I think you can use set default, right, with object 1. So set default is basically if it doesn't exist, create something. So set default, you also have like what's the default, and you have a list, an empty list, and then you append it to this list, you append object 2. All right, so maybe let's add this one. We can type him, so append appears here, and you do like this. Now let's see if is there an issue here. No, it's not. There shouldn't be an issue. Okay, so we go back. Now we have let's say collisions. Let's get collisions objects, or scene objects actually, and now we can change this, so we don't have colors anymore. At least we have, but not in this way. So let's say color is black, actually color is red if object is in collisions, else it's black. And this is basically the same thing, but now the main function is just a call to this get collisions, and then we check. So basically we make it red if it's colliding with anybody. So it is colliding with anybody if and only if it is part of this dictionary that we created here, because that's the only way. So if any object is colliding with any other object, we create a dictionary with a key itself and a list of all the other objects. So the color here is basically, are you or not colliding with anybody? We can even get rid of this thing, and this one should still work, right? All right, cool. Okay, so another thing that we can do now is we can add new objects, right? So we have added, and we only have static objects, but the simplest way we can add is basically create a new circle if you click somewhere on the screen. So in order to do that, you have a bunch of options. So the easiest way that you can do is basically you can use the raylib or is key pressed, or actually is mouse button pressed, and you have mouse button left, I think. Yeah, so if it is pressed, right, what do we do? Basically, we know the mouse position is this, and we can basically just say scene object of append. So we create a new one, and we use this scene object construction, and now you can use mouse position, text mouse position apply, and the radius is, maybe we have a variable called mouse radius, which is 30. We use it here as well. Mouse radius. So don't really like a lot of the magic numbers, and when you do this kind of graphics programming, you have a bunch of like magic numbers, but yeah, it is what it is. So now technically if I press click, yeah, there's a new object created. So if I create one on top of another existing one. For example, here, as you can see, they're always colliding now. We cannot remove items at this moment. We can only create, but basically this allows you to like create objects. Another thing that I want to do is maybe add some FPS counter, and actually really provides you with some ways of doing that. That is very easily. You basically have this function called draw FPS, and you put position X, position Y, and it's very nice because it like has like colors and so on. And you can use the width, get screen width minus 100. So this is like enough space for the FPS text, and the position can be like 100. They mess this up. No, okay, it's a bit too down, so maybe put it like in 30 here. Okay, actually maybe it's 0. All right, so it works with 0. I thought, I don't know what was in my mind. One thing that's a bit nasty is that you can basically draw on top of it, but yeah, it's fine. We will like make a small fix for that a bit later on. But what this allows us to do is basically to check the FPS. And for example, we will see that if we keep adding objects, because of this open squared implementation that we have, like the FPS just keeps dropping, and it will drop dramatically because like all the time you need to do like this open squared thing, right? So you have to check each object against each object against each object, and so on and so forth. So as you can see, like right now I'm at 15 FPS. So basically it goes down, and at some point it becomes unusable. It went up. I think this is because of Python probably doing some stupid thing, because yeah, it's not like a system programming language, but it's fine. Cool. Okay, so we have an option to add new objects. All right, so the next thing that we are going to do now is basically like spawn a bunch of random circles, and we want to actually see how many collision checks we are doing, so we can like counter this quadratic problem that you have with this check collision function, and we want to see that it actually scales, you know, like that, and that. In order to do that, we can basically create some random objects here. So let's maybe make this maybe, yeah, create like a variable called an object, which could be like 30, and basically we iterate on that. So any objects, and we should create like one new circle basically at random, somewhere spawned here in the screen. You can also add another thing here, because we want to create these circles only inside maybe a scene, let's say like a square. And in order to do that, the best thing we can do is to create like a window size, probably, or scene size, however you want to call it. Maybe scene size is better. Scene size, and let's say that 600. So it should be like slightly smaller than the window, because maybe, yeah, we want to keep the FPS somewhere outside of this window. We like create like a small border and say, okay, things inside the border are inside the window or inside the scene. Things outside are maybe like the AGD or something like that. All right, so for example, we could create objects of random radius, so that would be random.randint, so let's say between 5 and 35. All right, we should import random here. And if we want the object to be inside, it means that the radius on the left side should be, basically the object should start at the radius. So the X position will be like between radius and scene size of 0 minus radius, because otherwise some parts of it will be outside. And on the Y position, it's basically the same. So we can do scene object append, scene object, circle, X, Y, radius. And I think that should be correct. Let's see. Main. All right, so we created a bunch of them. None of them seem outside, and these also seem like to be below the 600 thing. So maybe let's actually draw the rectangle over there as well. What's up with this? Maybe I should annotate it in object. Yeah, and let's also draw like a small rectangle here. So draw rectangle. I think you have to use draw rectangle rec or draw rectangle this one is a bit, draw rectangle lines X. Okay, that's it. And you need to provide top, left, bottom, right. So it's 0, 0, and there's a tuple. So 0, 0, scene size of 0, scene size basically. Now, why I want to do this is because I want to make it a bit thicker. So maybe it's thickness 2, and it's just 2. And now, okay, we have that. I was a bit afraid, but this is actually the mouse that was outside. Now the problem with this is that I still can create objects outside. So we probably need to also change the check that we cannot create objects if they are outside. So in order to do that, we need to update this here thing. So basically what we need to do is to do the, mouse position X, this is a small box, so it should be mouse position Y. But we also need to do the following. So basically mouse position of X plus radius, right? Or yeah, if this one plus, so basically we need to do the same thing as here. So if it's minus radius is smaller than 0, or plus radius is greater than scene size of 0, yeah, this, or the same on the Y side, then you cannot do that. So maybe yeah, we should probably do it the other way around. So it's greater or equals mouse position of X. I want it to be inside the screen, so that means, all right, this one is giving me a bit of a pain. Is smaller or equals than scene size of 0, and all of this should be with N. So this one, like this. Only then you can draw this. Okay. I'm not sure if this is correct, so let's see. Okay, cannot do it like that, cannot do it like that, cannot do it like that, but inside, okay, inside it works. Cool. Okay, okay, so I wrote it correctly. For some reason I got a small brain part over there. Cool. Okay, so that works. All right, so we got it. Yeah, the next thing that I want to do now is to actually see how many collisions there are happening. So in order to do that, the simplest way that you can do it in Python is create a global variable. It's much easier than anything else. So let's just call it collision checks probably. Let's call it like that. So every time you start the loop, you do collision checks equals 0. And I think in Python you need to do global collision checks. All right, and then this function, every time you enter it, so actually this one, check collision, every time you are here, you just append 1 to it. All right, so this means that every time we call this function, we would get +1, and this resets every time, at every frame, at every render tick. But because we call get collisions here, this would showcase us that we are doing this often squared, where each object is checked against each other object. But we should also like draw that thing. So for example, get collisions. Most of get collisions can be outside of the draw function. Usually you want to have like your render stuff on one side, and maybe you want to have like your IO and update stuff before. So something like this. good. So we have these collisions here. Now we want to draw. So maybe yeah, we want to draw this text. So in order to do that, there is this function called draw text, which actually accepts text position. So the position can also be something similar to this. We need to put it a bit below the FPS. So maybe let's do it at 100. The font size, I don't know, we need to check that, and then let's get it black. Let's have a random text first. You also need to do this totem code. You want, because it needs to be ASCII, because this is calling like it basically it requires bytes. It doesn't understand like Python strings, so you need to convert it to basically bytes. All right, I think it's good, but it's not perfect. So I think we can do minus 150 here, and this one should be a bit higher. All right, because what we want to do here is basically the following: collision checks, right? This is what we care about. And that's maybe too much, maybe the text is too big. How do I do this? Maybe 200 here. Okay, that's a bit ugly. 195 and 18. All right, 20. Incredible that 20 is so big and 18 is not. All right, I guess that's fine. It's a bit ugly, but it says 900 and something over there. Maybe we also need to see how many objects do we have. So let's say 16 objects. So we have 31 objects and we have 930 checks. Does that check out? So for example, if I do 30/31, 961, because it's 961 minus 31, because we always skip if the object is checking against itself. So that checks out. So now if we add one more object, for example, it's 992, 156, and so on. We can check that with fewer objects maybe. So instead of 30, let's try with 3. So that actually it's 4 objects. Because of the mouse as well. So actually maybe we should fix that. So because we always add the mouse here at the end, spatial mouse, we want to have -1. So basically we have 3 objects, right? And we are doing 6 checks. Which does it check out? Yeah, it does, because it's 3 squared, which is 9, minus 3. And if we have 4 objects, it should be 16 minus 4, so it should say 12. All right, cool. Now, we have a problem here, right? So before continuing with the spatial hash grid that we want to implement, there is actually a small and very fast implementation or very fast optimization that we can do with the current implementation. So basically the idea here would be that instead of checking each object against each object, you can check the first object against the next ones, and then the second object, there is no reason to check against the previous one, because the first one checked against the second one, so the second one should not check again against the first one, right? Because they have already checked. So that means the ith object should only look forward and never backwards, in the sense that the previous object probably checked for him. So in order to do that, there is a very simple way. You just start from the i+1s here. They cannot be equal anymore, simply because you are never doing that. You're only skipping, so that means there is no point of having this variable at all. And if it turns out that they are colliding, then you add both of them at the same time. And that just halves everything. It's still often squared, but it's just much, it's just better. So let's see if that works. So now, as you can see, we have 3 objects, and there's no 6 checks anymore. No, there's 3. And for 4 objects, that means there's only 6 checks. So how you can do this is basically it would be 4 times 3 over 2. So that's 12 over 2, which is 6. And for 5 objects, right, it should be 10, because this is what, 5 times 4 over 2, so that's 5 times 2 is 10. And that basically this scales much better, but we still have the same problem, right? So it still scales quadratically. So at some point, by the way, here we cannot add items. At some point you'll have the same issue, right? Like for example, for 100 objects, let's say if I want to add 100 objects here, I would still have 4,950 checks, because this is 100 times 99 over 2. And now we're ready to implement the hash grid. So basically the idea here is actually quite simple. We want to divide this scene, so this square, which we call a scene, into smaller rectangles, each of a specific size. They're all equally sized. And then we want to see in each, for each object in each cell of this grid it is taking part of. So basically, for example, if we were to have cells of, let's say, this length, so let's say that the scene is 2 by 2, presumably, and then each cell is a 1 by 1 square in this combination, then each object, for example, here, can be part of one cell, it can be part of 2 cells, so if it like borders, it can even be part of 4 cells. Now the objects can be arbitrarily large, and the cells, you know, they have a size. So there is also this possibility, right, that maybe the object is very big and your cell size are smaller. But the main idea here, as you can see, so for example, let's take in this case, this object is part of these 2 cells, right? And this other object is part of these other 2 cells. And the only place where they are interacting with each other, the only place where they could be colliding, is on this common cell. So the main idea here is the following. For each object, we find out in which cells it belongs to. So these 2 cells for the first object, these other 2 cells for the other object. And then we check only inside each cell for all the objects that belong to that cell. So basically what we want to do is the following. For object 1, it belongs to these 2. So for example, we'll create this data structure. All right, so in order to implement this, we will do the following. So the first thing is we need to detect for each object what cells it belongs to. And this is basically a dictionary we'll be creating, which will, so the keys will be like this index, and the index represents basically the number of the grid, or the number of the cell. So basically this is the first cell, this is the second one, this is the third one, this is the fourth one. And this will be computed based on how big it is relative to how big the scene is. And then for each of these, we will have like a list of objects. So for example, object 1 and object 2 both belong to 0, 0. For 0, 1, it's only object 1, and for 1, 0, it's only object 2. That means this particular cell has no object, and it means that we don't need to actually store it. So actually what we will return from, let's say, a function that we will create immediately is basically these 3 things. Yeah. Now, how do we know in which cell an object lives? That's a good question, right? So the simplest thing that we can do, and this is usually what happens in like games as far as I understand, is that you have like a complicated mesh for all your objects. So for example, you have like a player or whatever, like a player model. For example, I have this image, which kind of showcases this, and I hope this is not a licensed image. So basically, your model may have like a very complicated mesh, right? But when you are doing like collision detection, you actually simplify the geometry. So for example, you would use like the bounding box of this object, because it's much easier to make collisions based on bounding box than on arbitrary shapes. This is very similar to what we are doing here. For example, instead of operating on a circle, we'd rather operate on the rectangle that basically extends from the circle. So this is a bit bigger than the circle itself. And in order to do that, you just need to get like the top left and bottom right. So to do that, you go from the center, which you have access. You also have access to the radius. So this is the radius, and you go on the diagonals. So top left and bottom right. And this is kind of the rectangle that that overlaps over your circle pretty much. Okay, so let's implement that. So basically what we would like to get here is a variable, let's call it grid, which I just like to call this function make grid. And we just get all the objects, and we need to get like this cell size. So basically, how big is each cell? This should probably be smaller than the scene. So for example, the cell size can be 150 to 150. That means we will get 16 cells, right? So 600 divided by 150, we get 4 on each x and y. They don't need to be equal, so the x and the y don't need to be equal, but it's like easier for visualization. So this function will return, as I said earlier, like a dictionary. So make grid, we'll get what the objects. Okay, let's just call it screen object, so it's the same as above. In grid size, cell size, I'm sorry, it will be just a tuple. Okay. And this one, as I said earlier, should be the following. It should be like a key. So let's follow this, right? So the key is like the index of each cell, right? So it's from 0 to how many cells you have. So in our case, it will be from 0 to 3 on the X one, and from 0 to t, because there are 16 in total, right? For the variables I chose earlier, which is 150 length. So we will have like 16 cells from 0, 0 to 3. All right, so that means we will put here like tuple, int, and then we'll have like a list of objects that belong to that particular cell. Cool. Now, how do we get the actual? How do we get the cell in which each object belongs to? So, in order to do that, so let's take this variable here, which this type. Okay, so we go through each object, for object, instant object. All right, so we need to get the bounding box, which means that we need to extend to the left and to the right. What I like to do is I like to basically have two variables, top left and bottom right, and we can have a method in that class that we did earlier. So this way we would be able to do the same for different type of objects. So we don't like hard code one just for the circles. So this is the D box, and it should return like top left and bottom right. So this is like tuple, float, tuple, float. So top left. So each cell of object is circle. Will be what? Will be self. So we have radius and center, right? Center and radius. And this will be solid arcs 0, 2, solid arcs 2. This will be center minus center of 0 minus radius, center of 1 minus radius. So this is going from the center all the way to the diagonal on going up, and the center bottom, right? Which will be right, and we can return top left and bottom right, and that's pretty much it. Cool. So we have top left and bottom right. Now, what do we do with it, right? So that's the first question. Go back to this. So we have top left and bottom right, but let's not forget that you can be in this situation as well. So top left will be here, bottom right will be here. So what we need to do is that we need to iterate through all of them, right? We need to iterate through all of them. Okay, so before continuing to implement this grid function, I thought it would be better if we were to actually draw the cells first, right? So we have a scene size of 600 by 600, and we have a cell size of 150 by 150. That means we have in total 4 cells. And why not draw them first, and then we can like continue implementing the grid and the objects belonging to each cell. So basically what we want to do is figure out how many cells there are on X and on Y. So for example, let's call this an X and an Y. And we need basically to do the following. We need to do 600 by 150, and this gives us 4 cells. And this is the same on both axes. But for example, if the screen size were to be like a bit bigger, for example, it's kind of 30, then we will need this to be 5 cells, right? And the last one is a bit like trimmed, but it doesn't matter. We have like 5 cells in total. So in order to do that, the easiest way to do is basically using mass.ceil, which is basically mass.ceil of 4 point something, I don't know exactly, 4.3, which goes to 5. So this is done by matplotlib since type 0 to cell size 0, matplotlib all right, and then we iterate for I in range x for j y. Now we need to draw basically small rectangles that are of cell size. So basically what we need to do is the following: radius.draw rectangle, and it starts from where? Starts from I times cell size of 0, right, and j times cell size of, okay, and it is of cell size with the with no color, because it's not a draw rectangle, it's draw rectangle line. Yeah, and I think we have the same, and then we have gray black. So let's see if that works. It doesn't, because there is a bug in this thing. It returned none. Oh, because I had the small title here. All right, tuple out of bound, cell size of 1. All right, cool. So we basically drew all of this. So now let's also put some titles here to know which cell this is. So in order to do that, basically what we want to do is to basically just reuse I and j. So draw text. So the text is basically what? It will be I, j, maybe with comma in between, dot encode. The position of x will be basically this. Position of y will be this. The font size is maybe 12, and let's just black. Okay, that's a bit too small and a bit too, so maybe 16. And maybe we also need to add like a little bit of +5. All right, cool. So we see that this one is the first cell, this one is the second one, this one is the third one, and the same on this other side. Now, okay, so a small interjection over there. So what I wanted to say, but I had to cut off because I messed something up, is that after we have created those labels, these labels are basically the index of each cell. So this is 0, 0, this is 1, 0, this is 2, 0, and so on and so forth. And this is basically done by dividing the position of this point by the grid size or by the cell size. And this is what we are going to use as an index in our hash grid. All right, so now we have this cell ID, basically, or the cell key. Let's actually get all the objects that belong to each of these cells. So in order to do that, we can actually basically use the bounding box that we computed earlier. So that's just the radius went in both diagonals. And what we need here to do is the following. We need to get the first cell and the last cell. So the first cell is literally just top left divided by the grid cell size. We can also put an int here, and it's top left 1 divided by the cell size of 1. And the last cell is the same, but on the y bottom right. This is, I'm sorry, 0, 0, bottom right. So in order to do this, maybe let's actually print the position of the mouse and then the cells it belongs to, just to see that it's properly computed. So in order to do that, we know that the mouse is the last object. So if I equals the last object, then we do the following. We can print the x position. So x is first top left. Actually, that's just top left. Then we have bottom right, and then we have first cell, and we have last cell. All right, so let's see how that looks for the moment. It doesn't print it. because yeah, this is supposed to be -1 here. Okay, cool. So let's see if it's properly computed. So for example, if we are at the beginning here, the top left is very small, so it can actually be negative, as you can see. So the top left is very small, the bottom right is very small. Now the first cell and the last cell are basically 0, 0, which is exactly what we know. So now if we cross over, we can see that the first cell is 0, 0 and the last cell is 0, 1. That means it properly computes it. It's the same if we go on the right. So the first cell is 0, 0, the last cell is 0, 1. And if we were to cross like all four of them, that means the first cell is 0, 0, the last cell is 1, 1. So we can see that this works, and basically we are able to know in which cells each object belongs to. Cool. Now using this information, basically what we want to do is to iterate from the first cell to the last cell and just add it to this rest variable that we created. So how do we do that? We actually need to know how many cells it covers. So we can actually use the same trick as before. So last cell minus first cell plus 1, and this will be on the 0. Why plus 1? Because yeah, we want to go inclusive to the last cell that we go to, and this is the same for the y coordinate, and this is my. For I next for j y. And basically the key here is the following. So this is the key. That means in which cells this thing belongs to. Because we did this from last cell, we need to add basically the first cell. So that means this is first cell of 0 plus I, first cell of 0 plus j of 1. Okay. And we also will use the same trick as here. That means if this cell has no object yet, we create a default. So the set default key nothing, and then we add this particular object, which is object. And I think that's all. We iterate through all the objects, we iterate to all the cells it belongs to, and then we add the object to this result dictionary. So let's just return that. And that is the grid. Cool. Now what we can do with it, because we are already iterating and drawing the grid, we can do the following. Let's change the color of this grid if there is any object in it. So in order to do that, the simplest thing we can do, because we're already drawing the lines, that means we can also do something like draw a rectangle. Yeah, and if basically ij, so let's not forget that ij is also the key. So if there's any item in that cell, if there's any object, that means it will be part of this dictionary. If there's no objects, again, like as I said here, if there's no objects, we don't return it. And this happens by default because we don't add anything, we only add items to this dictionary if there's any object in that cell. So if ij, is that correct? I think so. If ij in grid dot is, then we draw it, and let's draw it with some random color, maybe 100, 0, 100, 100. So it also has a bit of transparency. And as you can see, it will draw only those cells where there is an object. And if I were to like move the mouse around, like because this particular object is the last object and we create it at every frame, it allows us to like check that this is correctly implemented. It also works if you go outside of it, which is very good, right? All right, so now we have the list of items in each cell. And now comes basically the crux of this video, and all of this was like a build up for it. So since we know each object in each of this cell, even though sometimes there are an object is in multiple cells, it doesn't matter. We return from the point of view of each cell. Now, what we can do, and this is basically what we want to do, is instead of checking each item against each item, so instead of checking this one here against this one here, we only check the items that share the same cell. So we go through each cell and then we only look and do this O of n squared thing inside that cell. So basically for cell 2, 1, we will only check this item against this item and see if they are colliding. For cell 1, 1, we will only check this item because it's the only one, or maybe the mouse is, or maybe we can add another item here. But basically we will never check outside of the cell. So this one will never go and check against this one. Yeah, so this is what we want to do. So in order to do that, we already have this grid thing, which returns us basically the cell that contains items. So what we can do here, instead of calling this function, which is, as you can remember, the O of n squared version, is the one that where we divide by 2, but it's still O of n squared. We will do the following. Okay? Say get collisions grid, and we just pass the grid instead. You know, how does this function look like? So for example, let's get collisions grid, and we get this thing. So this is the grid, this is the type of the grid. All right, and we return the same as here. So for each object, we return the list of objects it collides with. All right, so let's look at this function. Actually, let's even copy paste it because it's going to be very, very similar. So instead of going through all the items, now we don't have the list of objects. We have the dictionary of each cell and the list of objects inside that cell. So what we can do here, we go through each cell. So for cell string object in grid of values, for example, we don't even care about the key. And now this one is a list of objects, but it's guaranteed to be inside each cell. So we can literally just copy paste here. And to be honest, let's call it like this. Let's see if it works. It literally works, and this is what I wanted to say. Like, this function is so simple to implement. It's basically copy paste of the O of n squared one. And now let's look at the number of collision checks here, if you can look. So basically we only do like 3 collision checks in this entire thing, because we do one here, and one here, right? And that's all of these other ones, because they are empty, there is no other object, we never like check anything else besides these cases. As you can see, when I get the mouse very close here, so this is an interesting thing, there is like another cell here that's hidden, and when the mouse gets very close, you get like another collision check, which is this object against this object. That's pretty much it. There is a small gotcha that you need to be careful with. So the problem is that because an item can belong to multiple cells at the same time, and because we go through each cell, there may be a case where we get duplicates here as well. So basically we would get for object 1, for example, if it collides with object 2, and that happens across 2 cells, we will just get duplicates. A very simple way to get rid of this is just use a set here, and that's pretty much it. You also need to change the default here. So when nothing, when there's no object in one of these cases, and you need to use add instead of append. That's pretty much it. It works as before. Very interesting. There's 0 collision checks. Now, let's not fool ourselves. There's something that also happens here. So at every frame, you need to create a grid, and then you iterate through the grid and check for collisions. Before, you wouldn't do that. So the question here is there a trade-off? So when is it better to do one against the other? When is it more expensive to build a grid, and where is it more expensive to use the other one? And one way we can do this is we can actually like check. So for example, what we can do here is the following. Let's make a variable called collision type, and let's call it basic. So this is the O of n squared, right? And if we press on let's say F1, I like to use F1 for this. Let's swap between the two. So collision type is basic, if collision type grid, else grid. So basically you only have 2 options, grid or basic. And if collision type is basic, in previous code, let's use this one. Otherwise, let's use the other one. And let's also maybe add it here so we know. So this is the text that we've added earlier. So let's say collision type, collision type, collision type. So let's see if that works. Okay, there is a small problem on line 126, which is okay. So it does. Okay, so it doesn't know the grid. Okay, so yeah, maybe we shouldn't even draw the grid. So if collision type is grid, maybe we do that. Then is this? Yeah, this is no. Okay, so I think I need to actually move this whole thing here. Okay, okay. This one needs to go like that, like that. And all of this needs to go like this. Okay, so we only draw the grid if we're in that case. All right, so by default, okay, so we have 10 collision checks. And if we add the grid, we have one collision check because there's, I think, only this one against this one. If we were to put like an item here, we get two collision checks, and yeah, basically we explained this earlier. But now we have the ability to move between the two modes. And that's great because as you can see, we have 21 collision checks with basic, and we have 4 collision checks with grid. But still, there is a problem here that, as you can see, like the FPS is actually quite similar. And in some sense, like you even lose some FPS when you use the grid, and that's because the construction of the grid also matters. By the way, another lever that we have now with this collision checking through the grid is the grid size. Because if you think about it, like if we were to have a grid that is as big as the scene, then we have done nothing. We just computed a grid that has a single cell, and then we do the often squared one. If we have a grid that is too small, for example, then each object will be part of very many cells. And also, like, the grid construction probably should take more time because you need to go through all of these small cells. The ideal case should probably be such that each object is like unique or very close to unique and belongs to a single cell. In that case, as you can see, the number of collision checks is very small. But in this example, for example, if we had like a cell that was smaller here or here or here, then probably that would have been even better. Who knows? So in order to check that hypothesis, we can actually adjust this cell size because we have hard-coded it, and nobody says we cannot like change it. So for example, let's add F2 and F3. So with F2, we will decrease the cell size, and with F3 we will increase it. So basically, let's do it like the cell size equals cell size minus 10. And we also need to make sure that we don't go below 10. So maybe we can put like a maximum of 10. So you cannot be smaller than 10, and the step size is 10. And this should be 0. Cell size 1 minus 10. And it's the same in this case, and the maximum one should be scene size, right? We cannot go beyond the scene size. So scene size of 0, and this one should be with mean here. And it will be like this: scene size of 1, mean plus. Okay, so let's see if that works. So now we go to this mode and we press F2, and now our grid is getting smaller and smaller. As you can see, we also draw when it doesn't properly divide. And that's fine. Maybe we can like keep it, even though it's a bit ugly. So let's look now. We have 0 collision checks, right? Because nothing overlaps. But if we were to like increase this a bit, at some point we get 1 collision check because these two start overlapping, right? And if we make it slightly smaller, we have 0 collision checks and so on. By the way, the number of FPS is a bit deflated because I'm also recording this, and my computer is a bit messy right now. But I actually have a pre-recording where I did this trick, and I will explain to you exactly what I did in order to find out like what's the optimal grid size, because this is quite interesting, right? Like if we want to make this, for example, very small, okay, that looks a bit ugly, that probably takes a lot of time. But if you want to make it very big, that just degenerates to the often squared case, right? So if you go this, like we are now doing nothing. So this is like the cell is as big as the scene. So the trade-off here is how do you make this small enough but not too small such that it does the minimum amount of collision checks and the grid construction also doesn't take too much. That is the main question that we have to answer now. Okay, so as I said earlier, I did a bit of pre-recording because I wanted to control the FPS without recording. and it turns out that it is a bit more reliable to do so. This version is a slightly updated version of the same code. The only things I've added here is I've added a bunch of command line flags. So for example, I control the seed, so that means we can spawn the same number of objects. So it means the colors are a bit different, but it doesn't matter. So if I run this multiple times, as you can see, we just get the same items. And this is because I control the seed and I just put a default one here. So if you want to change it, we can put something else. And this is again reliable. Now if we put 42 again, we get the same object, the same spawning, because this seed is used before spawning the random items. We also have a flag, so basically it's basic versus a basic v2, I call it in this particular implementation, or grid, and this one are exactly the ones that I showed. So basic v2 is basically this one where we skip like half of the cells, but it's still often squared. I'm sorry, this one here, and the grid one is the same, as you can see, but it goes through the grid. So it's basically the same code. Yeah, I also have a cell size. So now cell size, it's also settable from the command line. And I have this other flag here, which basically stops the main loop after n frames. And why did I do all of that? Well, I did all of that because I have like another bash function or bash script here, which is called experiment.sh, where basically I go through one object, 10 objects, 15 objects, 100 objects. I go through multiple cell sizes, I go through multiple seeds, and I just call this function. I just call my script basically with these flags, and I store the results in this CSV file. So as you can see at the very end, we just store the values. And what are these values? Basically, I've added a perf counter, so basically time of perf counter exactly before and after the collision part. So the question here we are trying to answer is, what is the optimal grid size given randomly spawned object in this case? And by the way, we need to be a bit careful because in most of the games, probably your objects are not spawned at random, rather they are hotspots basically in your scene. So this is where like a bunch of objects are, this is where a bunch of objects are, maybe this is a forest and you have a bunch of trees, maybe this is like where the players spawn and so on. But assuming that the objects are spawned at random as it's here, the question is, what would be a good grid size? And the results kind of look like this. So let's open. So we have one object, 10 objects, 50 objects, and 100 objects. I have a linear and a logarithmic plot because both of them like tell some story. So for example, let's look at one object, right? So for one object, this would be the time. So the time is very small. This is the time it takes to check basically one object and colliding with nobody else because there is only one object. And as you can see, like the time here is basically how much does it take to call the grid function. So creating the grid is the only thing that happens here because everything else is the same. When you go to 10 objects, we already see that, okay, calling the grid, if the grid size is very small, takes a bunch of time. So it's better, and this is because we have just 10 objects, so this is like 45 checks, if you remember, like of the often squared one, where you like divide by 2. And as you can see, like the time is smaller if you have a very small grid. And when you have a very small grid, it means that you have very small cells. They are very, very, very tiny. And that means that your basically it takes more time. So the case that I'm talking about is the following. It's like you have something like this, very, very, very small cells. And basically the objects belong to a lot of cells, and you do a lot of redundant checks, you do a lot of duplicate checks and so on. And this is why it takes more. But as you increase it, like as you can see, you actually beat the often square algorithm. Now the story gets even better when you go to more objects, and this is what you want, right? You want an algorithm that scales good, scales better with like the number of objects. And for example, for 100, and maybe this is the time when we start looking at the linear plot, you can see like the often squared is worse even in the case of a small grid, but then it goes very, very fast and it kind of plateaus at around 100. So the cell size of around 100, it turns out to be kind of optimal for this particular size. And now the question is, what is this 100, right? And it turns out that this 100 is very, very closely related to the radius size. So actually to the diameter. And a good heuristic here, if you look it up, is to basically start your radius as your cell size based on the average diameter of your object. So if your objects are around 100 of shape, that means your cell size should be around 100 as well. And that's kind of the results. And this is what it's telling us. Like if you have a grid that is too big, that's not good. If you have a grid that is too small, that's also not okay. But if you have a grid that's roughly the size of the diameter of your objects, like the average diameter, that's probably what you want to do. And you can do that basically because instead of setting it here, you can like iterate through all your objects, and basically you can set it up. Okay, so in closing of this video, I want to discuss a bit about like next steps here, because obviously this is a very simple implementation, and it's so simple that I had to make a video for it, because instead of like doing this often squared thing, you create a grid based on the position of each items, you use the key as the position divided by the cell size, and then you just do the O of n squared but inside that cell for all the objects that are in the cell. Now there's a bunch of optimizations that could be done, and to be honest, I've done some of them, but I didn't include them in the video because not all of them are actually worth it. So one thing that I discussed earlier is that we have to use a set here, and the reason we use a set is because you may end up in the situation where two objects basically are in the same in two different cells. So that means you check them twice, or you check them multiple times. For example, you have cells that are very small, right? You would check the same object multiple times, the same pair of two objects. And I tried to actually have another variable here, something like already checked, and you have like the pair of two items. So if you check this once, it doesn't matter if you check them again or again, because they are not moving in this example, and these collision checks that you usually do assuming like a stationary thing. So if you check now and you check a bit later, but you are still in this collision check loop, nothing should change. Like your update loop should include the results of this collision check usually. And I've tried to do that, and I actually lost some FPS. So maybe the problem is that the Python is slow here, or you need some better data structure to see if two things are checked twice. But yeah. Now, another thing that's interesting is that, okay, what about 3D? Because yeah, I only showed like 2D. So basically we create a grid in 2 dimensions, and then we check. The question is, does this scale to 3D? And it turns out it does. And this is one very interesting thing that I found while working on this graphic stuff, is that you can have this, let's say, 2D playground where you work with this pretty much a sandbox, and you are allowed to do these small scale experiments, right? But then you can actually expand it to 3D by basically finding a place. So who says that you cannot make a 3D grid, and instead of having like top left on the x-axis, top left on the y-axis, you can add like another one which is top left on the z-axis, and everything that you receive here is basically a cell size of 3 dimensions and so on. So who says you cannot do that, right? Like if your positions are 3 dimensions, then you can have like small cubes. So instead of having cells, you have like cell cubes, right, in 3D. And I'm actually working on a physics simulator or a robotics simulator, and basically that was the main motivation for this entire thing, is that I wanted to optimize that particular project. And now let's make like a very small parallel about the code that we actually use there, which is a 3D case. So over there, we don't have like just scene object. We have like this thing, which is like, so this is the object, and this is like the collider, and this is very much similar to what we did here. So the object is like a circle, but it's but we basically use the bounding box of that circle because it's greater than it, and it's easier to have a top left and bottom right to figure out what cells you make part of. So as you can see, I do the same thing here. I use the bounding box of the collider, which is exactly the same thing. Then I use first cell and last cell, which is very much similar here, but we have like 3 dimensions stuff. So this is like NumPy array. So point 3D is basically a NumPy array of 3 items, and it's the same, literally it's the same code, just with one more dimension. And the check collision code right now, as it looks, it's absolutely identical, right? So if you look here, it's absolutely identical. There is only one difference, is that here I return the all the collisions of each of an item, and here I just return the first collision because I actually don't care in that particular case about all of them. It's much faster to like return early, but that's pretty much it. And yeah, it scales. Now, did it help? I have this end-to-end test on the other side, so I like profiling stuff. Yeah, and guess where I introduced these collision checks? Can you guess? Like, it was here actually, right? So it was such a huge drop. This is for 100 robots, and for 100 robots, the physics would take like almost 700 milliseconds. That's like almost a second, right? And the physics includes collisions and also includes some other movement stuff. And it just dropped like significant for 100 robots. It actually became usable. It was not usable before. And yeah, it was usable for 1 robot, for 5, for 10, even for 20 was good enough. But now you can actually run it with 100 and it's okay, it's not the best. And then we've also had like another optimization here, and like everything like slightly improves and improves. And now basically I have to use this log plot because yeah, like the performance got so much better here that I basically need to make sure it doesn't regress again. So this is why I use log plots. And yeah, I guess the main conclusion here is that you can do a lot of things in 2D, like in the sandbox environment. Like find a good approach for your, let's say, bigger problem. Maybe even if your game code, your simulator code is in 3D, doesn't matter. You can reduce it to 2D, use these perfect shapes, make like this perfect API, like do experiments, do measurements, like do all the whole thing, and then you can port it. And if your code is written in a distant way, you can literally just find and replace 2D with 3D, adjust a bunch of things, and you should probably get the improvements that you are looking for. At least it worked in my case, and I hope it continues working. Yeah, thank you for watching, and yeah, bye.